Hi everyone, I'm Charles, and today I'm going to, dive a little bit deeper to, Trellis. I'm going to give a tutorial. Um, so again, you've seen this slide for several times in the track today. So Trellis is a multi-purpose leaf spine fabric designed for MV. It's based on open source software, white box hardware switches. It's pure SDM based, and of course, it's based on Honest. So there are several features we have in Trellis, but today I'm not definitely not going to cover all of them. So the features I'm going to walk through during the tutorial today is the basic bridging, routing, VLAN, and L3 DHCP Relay, and VRouter configuration. The things I'm going to exclude are something like IPv6 dual homing, and we have more and more features in development right now. So for the features I'm going to go through today, I'm going to take you through all the configuration in detail, like explain every configuration you need to enable this feature in your environment. So a little bit prerequisite. I am preparing this talk assuming that you guys all have some basic knowledge about Honest, Mininet, DHCP server, as well as Quagga and BGP. But if not, it's okay. I try to explain as detailed as I can, but due to the time limitation, I'm not able to go through details or all these stuff. So I'm going to focus on just the configuration of Trellis. Okay. So this is the demo topology I'm going to use today. As you can see, we have 2x2 leaf spine fabric, the blue switches. And then I have 4 hosts, 2 on the left-hand side, the other 2 on the right-hand side. So notice that the 2 hosts on the right-hand side are actually connected to the same physical port. This is a very common use case when you have VMs, when you have multiple VMs or containers on the same physical host. You were attached to the same port on the leaf switch. And then I also have several special devices here. As you can see on the right-hand side, there are the green boxes are the Quagga, and also I have an upstream router. I'm not sure if you can see my pointer here, but hopefully you can. And then I also create this RH1, which is a remote host that's sitting behind the upstream router. So I have a Mininet script that emulate the entire environment. So I'm going to run the demo, including Honest, including Mininet, and all the topologies in this single laptop. So I'm going to show you it's very easy to bring it up if you want to try Trellis. I'm also having this DHCP server over here. So I'm also going to configure that such that the host can obtain an IP address from this DHCP server. Okay. So let's get started. The first thing we are going to configure is the for the devices for the switches. So for each switch, no matter it's a spine or a leaf, you're going to see a similar configuration like this. So first, you're going to the first line here is that you're going to specify the DPID, the data path ID of this switch. And then there is a name. So unfortunately, this is actually not very useful. This name doesn't really matter, actually. But if you look down a little bit, there is another name over there. That's probably more useful. I'm going to talk about that. So this name over here, we actually plan to deprecate that in the future. Okay, then this one is important. The IPv4 node SID. So this SID is the segment ID of each switch, as Saurav and others talk about. We use MPLS routing in Trellis Fabric. So in order to do that, we need to identify each switch with a segment ID, and that segment ID will always will also be used as the MPLS label we put in the MPLS packet. So this segment ID can be an arbitrary value, but it has to be unique across the entire system. So you cannot assign the same ID for 2 different switches. But just to, as I mentioned, this will be used as the MPLS label. So a tip here is that do not use a reserved MPLS label, which is less or equal than 16, as your node SID. That probably won't work. What we usually do is we use a larger number, like 204 should be okay. The next one is a IPv4 loopback address. If you have experience with traditional network devices like Cisco routers, you can assign this loopback address to the device and you can ping this loopback address. Here in SDN environment, it actually doesn't have some very strong meaning, but you can still try to ping this address. What we usually do is that we put the management IP as the loopback address of this device. Also, it can also be an arbitrary, private IP address, just to make sure you don't assign the same loopback address for different devices. Router MAC is probably the most important thing here, because the switch would the host would now ARP for its own gateway, which is the switch, right? And then the honest or the switch now need to reply that ARP message. So what MAC address honest will use to reply the ARP from the host? It's this router MAC. So it can also be an arbitrary value, but also to make sure it's unique across the system. What we usually do is that we put the management interface MAC address here. That should be okay. The next one is edge router, which is pretty trivial, I guess. It's true for leaves, false for spines. Just SID, we don't use that right now. It is something we kind of left over from the previous implementation. So it's currently unused. You just need to put an empty array over here. And then next is the name. This is the name that does matter because this name will show up in the GUI. So you can on this GUI interface, you can see this name of device. So this is probably the more important name here. And then the driver. So as you see, we support different. We support like OVS emulated environment. We support OFDPA for Trident and Tomahawk based switches. We have Qumran based switches. They all require a little bit different pipeline design. It's still the baseline is still following the OFDPA pipeline design, but there are several small difference. So we have to specify different drivers for them. So right now there are several options. We have OFDPA OVS driver if you want to try Trellis in Mininet using OVS. OFDPA 3 is the default driver for Broadcom XGS family, including Trident 2 and Tomahawk. A QMX OFDPA 3 is the driver for Broadcom Qumran MX family. So in this example, since I'm going to use Mininet, I put the OFDPA OVS driver here. Okay, I hope this is clear to you guys so far. So we're going to need this device block for each device in this system. So I will go through the whole configuration file at the end of this talk, and we're going to see 4 similar blocks for all the devices. Okay, and then I'm going to talk about the port configuration. In Trellis, we need to configure each edge port that goes to a host, a server, a router. We don't need to configure spine, the ports between spines and leaves. So there are 2 things that's important in a port configuration. The first one is the VLAN. The second one is the IP address or the subnet configuration. So I'm going to start with VLAN. If you look at, I have a part of the demo topology on the top right corner. So in this example, I'm going to first configure the port of OF204 port 3. So here you would need to put the DPID/port number here, and then on this port, I assume that there is a on-tag host with this IP address. So we have 3 valid VLAN configurations, which are on-tag, which is the one I'm going to talk about in this page. And we also have tagged, and we also have tagged plus native. So for on-tag traffic, if you're familiar with traditional network, this is essentially equivalent to access port. What VLAN on tag 20 here means is that we're expecting on tag packet coming into this port, and we are going to assign VLAN ID 20. We're going to push a VLAN header and assign VLAN 20 to this port. This is exactly the access port behavior. So we call it VLAN on tag. So I think in some system they call it access trunk. The other system they call it on tag tagged. But anyway, we have a kind of argument about what name we should use, and we eventually decided to use this one. The next one would be VLAN tagged. So as I just mentioned, this is equivalent to the trunk port configuration, which means that on this port, we're actually expecting a tag packet coming in. So if you can see on the upper right corner, on port 4, we actually we have the host with the VLAN tag 20. So we need to make the port number 4 a trunk port. So just like other trunk port configuration, you can have more than one trunk VLAN on a trunk port. Right? So this is an array instead of just a single value. In this example, we just put one VLAN ID, which is 20. So this means that we're expecting packet coming in with VLAN tag 20, and then the Trellis will keep that VLAN tag, in the pipeline until it goes out. So when it goes out on an egress port, we can later on decide, according to the egress port VLAN configuration, we can decide whether we want to pop the VLAN or keep the VLAN. And that's the different story. I'm right now talking about the ingress part, when the packet arrives the switch. Okay. We also have tag with native. So this basically means that we accept both tag and on-tag traffic on this interface. So in this example, we have VLAN tag 30, means that we accept packet with VLAN tag 30 coming into this port, and we're going to keep the VLAN 30 and going through the pipeline. We also accept an on-tag traffic or a native VLAN, on-tag traffic or on-tag packet coming into this port. And in that case, we are going to push a VLAN header and assign VLAN 40 to that packet. So with this configuration, we can actually support both tag and on-tag packet, just like a traditional trunk port with native VLAN config. Is it clear so far? Okay. Now I've done the VLAN part. I'm going to move forward to the subnet. Okay, so here you can see I picked this example port 205, switch 205 port 3 as an example because I attached 2 different hosts within different VLANs and different subnet in this example. So I want to using this more complicated example to explain what the subnet and VLAN means here. So as you can see, we actually put 2 IPs here. The IP configuration in this section actually we can derive 2 information from a single string here. So if you look at this one, 10.03.254/24, it actually means 2 things. The first thing is that the interface IP of this switch port is 10.03.254. This will also be your gateway IP for all the hosts that attaches to this port. Okay, and then the second thing we can derive from this configuration is that the subnet we expect to use on this interface is 10.030/24. So we actually, this string actually combines 2 informations here. Okay. a special note I put here is that currently we don't actually have the mapping between subnet and VLAN. So usually in the traditional network, we map one VLAN to one subnet, right? And if you're going to use a different VLAN ID, you will probably have a different subnet. But we don't currently implement that one-to-one mapping in Trellis. What does that mean? That means that the VLAN information in Trellis is solely used for defining a bridging domain. So when you have Trellis would define a bridging domain according to the VLAN configuration. And when it comes to routing, it only look at the IP or subnet configuration. So I understand that there are some confusions here. A lot of operators actually ask us to try to improve this a little bit. And I would say this is already in our plan, and we are going to, change it to a one-to-one mapping in the future. So yeah, that's it for subnet. Okay. Is everyone still is everyone still following so far? Because I've go through a lot of things, but if you have questions, I think you can just ask. Okay. All right. So I've gone through the device config, the port config, and that's actually the basic configuration you need to run a Trellis fabric for basic bridging and routing. The next one I'm going to talk about is actually an advanced feature we introduced recently. It's the L3 DHCP Relay. So without this DHCP Relay support, you need to configure IP address on each of the hosts. And you also need to configure route and default gateway on each host, which is very annoying when deploying in a real environment. So we introduce this DHCP relay such that you can configure all the hosts to use DHCP. And when they send the DHCP to the switch actually packet in the DHCP request to Honest. Honest then directly packet out that DHCP request to the DHCP server. In this case, and the DHCP server will reply, and the reply will also go back to the host on the same path. And in this way, we can support DHCP on the host, and the host can get the IP address from the server. In order to use this feature, we need just two configuration, very simple configuration. The first one is that you need to specify the location, or what we call connect point in Honest, the location of the DHCP server. And in this case is switch 205 port 6. The second thing you need to specify is the server IP. The IP of the DHCP server in this example would be 10.03.253. Well, unfortunately, the IP of the DHCP server must be static, so you still have to configure one host, which is the server itself. So yeah, this is the only things you need to, on the Honest side, the only two things you need to use DHCP. But you also need some configuration on the DHCP server side in order to know which IP pool you can use. But this is exactly the same way you configure DHCP server in a traditional environment. You will need to specify the subnets you want to assign. You need to specify the range of IP addresses you want to use for DHCP. And also, you can have this option routers in order to announce a default gateway to the host in the DHCP message. So once the host gets the IP address, it also gets its own default gateway, so you don't have to set the gateway. And also, just like traditional DHCP configuration, you can have static DHCP config. You can map a MAC address to a fixed IP address. This is also possible. Okay. All right. This is all about DHCP config. The next one I'm going to talk about is VRouter, which is the feature you use to peer with the upstream router and talk to the outside world. So in order to use VRouter, the configuration on the Honest config side is also very simple. What you need to do is that, so I'm going to switch to the next page just to look at this diagram. The only things you need to do is that you need to put the Quagga and the upstream router in the same bridging domain so they can talk to each other. In order to do that, again, you need to use this port configuration in the port configuration I introduced earlier. What you need to do is that you need to put Quagga and upstream router in the same subnet and VLAN. So in this example is we use VLAN on tag 10 and also this subnet 10.0.1/24. I use /24 in this example, but actually the minimum subnet you can use is a /29. We only need 3 IP addresses in this subnet. The first one is for Quagga. The second one is for upstream router. And the third one is actually for the leaf switch interface. Why we need this one, I will explain that just in the next page. So yeah, you can use /29 for IPv4 or /125 in IPv6. But since this is any private network, so actually it's okay if you use a bigger subnet. It shouldn't matter. Okay. Now this is a little bit tricky part of the current VRouter implementation. So what we are trying to do here is that we only want the BGP traffic to go through Quagga, right? Because Quagga is a software component, and we definitely don't want the data plane or routing traffic to go to Quagga, right? So what we do here is that if you see the diagram, we are going to bridge the BGP traffic between upstream router and Quagga. However, we are going to route the data traffic directly on the data plane using the hardware switch. So this will give us better performance, and of course, we don't want any traffic to go through Quagga to create another header pinning problem Saraf mentioned earlier today. So in order to do this, the trick we use is we call route map. If you're familiar with BGP, you probably know this already. The purpose of route map is that the Quagga will announce the leaf switch, the 10.0.1.254 IP address, as the next hop instead of Quagga itself. Okay, so when the upstream router tries to route a data traffic to the fabric, it will actually put 10.0.1.254 as the next hop. And then when that traffic hit the leaf switch will route it directly, to the destination. Either the destination could be on the same leaf switch, or it can go across the spine and go to another leaf switch. And that will be done on the data plane. So in order to configure this route map in a Quagga or BGPD configuration, there are several things we need to set up. The first block here is the list of prefixes we want to announce. In my demo topology, my internal network is 10.0.2 and 10.0.3/24. So I need to add these two subnets into the prefix list. And then the second section, I'm going to define this route map. I just give it a random name. I call it next hub 41. It actually means IPv4 and peer number 1, but it actually doesn't matter. It's just a name. And then I applied the route map to I applied the route map to the prefixes in this prefix list, which I defined in the previous section. And then for every prefixes in this route map, I'm going to set the next up to 10.0.1.254, which is the leaf switch instead of Quagga itself. Then there is neighbor configuration, just like traditional BGP. We need to configure peer information and peer AS information. The important part is here we need to set the route map to use the previous defined route map and push that to the peer, which is the upstream router in this case. We also have a block, like it's a typical configuration. We have a block to define what networks are reachable from Quagga. So yeah, route map is the probably the most tricky part if you want to configure the upstream router. But with this example, I think it's easier to understand how to do that and why why we need to configure a route map and announce a different next up. Okay, is that clear to everyone so far? Okay. And then I'm just go through the things about BGP, but once the Quagga receive the BGP information from the upstream, it still has to talk to Honest to let Honest understand, I receive a route from the upstream. So this is what's going to happen. So the first step is that the Quagga is going to receive a BGP route from the upstream router. And then the Quagga will talk to Honest through a FPM channel to push the route it learned from the upstream to Honest. Honest would then use OpenFlow to install the flows to all the switches. Well, actually, it shouldn't touch the spine. You only touch the leaves. On the remote leaf, this one, Honest will install a flow that says if you want to go to the subnet of the announced by the upstream, you need to point to this leaf switch, the leaf switch on the right-hand side. And on the blue leaf switch, Honest will install a flow saying that, if you want to go to the outside world, you just go out on the upstream port, this one. Okay. So in order to set up this FPM channel, we need to put something in the Zebra D configuration. The first line is actually optional. You can set your default route to management network, or according to your deployment environment, it could be a different default route. In this case, I point my default route to the management network, but I only announce a smaller /24 as the upstream. So the second line is actually more important. That's the FPM configuration. So we need to put the Honest instance IP address here. And that address need to be reachable from Quagga VM or container or server. So yeah, that's the FPM configuration we need. Oh, actually, that's it. That's all the configuration I want to talk about today. So the mininet script that generate this topology, as well as the configuration, the entire configuration file, I try to break it down to several parts, but the entire configuration file will be available at this link after this event. So, I've done several last-minute modification to the script, so I haven't pushed the latest one to get it, but it should be available pretty soon. Now, before really showing you the demo, I want to, just quickly go through like what's going to happen here, right? In a demo, for example, I will try to ping host 1 from host 3. And this is what's going to happen, right? The host 3 will try to first send the ping packet to, well, actually before the ping, it will try to ARP for its own gateway, right? And the leaf switch will reply with the router MAC. That's the first step. And then after it resolves, is it out? Oh, okay. After it resolves the MAC address of its gateway, it will try to send this ping packet, right? So the ping packet will coming out. Notice that this host is configured with VLAN 30. So the packet will come out with VLAN tag 30. It will reach leaf switch 205. And this packet will have a source MAC as H3, the MAC address of H3. The DAS MAC will be the router MAC of switch 205. The source IP will be H3 itself, and since I'm trying to ping H1 on the other side, the DAS IP will be H1. Now, when you reach the switch 205, the switch 205 will actually try to hash this packet to either of the spine switch. So in this example, I just assume that we pick the ECMP algorithm pick 226. Okay. So in this case, when a switch 205 trying to send this packet to 226, it will actually push an MPLS header to this packet. So the source MAC of the packet will become 205. Des MAC will become 226. And here we have an MPLS label indicating the target leaf switch, which is 204 in this case, because host 1 attaches to 204. And then we're going to, the source IP is still H3 and the DES IP is still H1. So we do routing and we don't touch the source and DES IP. We only swap the MAC address at each hop. So when the packet reach the spine switch, it will look up the MPLS label and understand that, oh, I want to reach 204. Then I have to send out from this port, right? So it popped the MPLS label, set the source MAC to itself, source MAC to 226, the DAS MAC to 204, and then send it out on the port that goes to 204. So at this point, this packet returned to a pure IP packet again because the spine switch popped the MPLS label. And then once the finally, when the packet arrived 204, you just look up the routing table and realize that, oh, my target H1 is here. So what switch 204 will do is that we will have a flow there that set the source MAC to 204, set a DES MAC to the H1 MAC address. The source and DES IP still remain the same. And then send this packet out from port 3 in this example, and you will arrive host H1. Okay. So yeah, this is what the basic thing we're trying to look at during the demo. So okay, let's start the demo. Let's see. Okay, this is probably a little bit difficult to see. Let me try to adjust this a little bit so everyone can see that clearly. Sorry? Okay. I think we should probably first look at the entire network config file. Okay. I try to make it larger so people can see it, or no. Hold on. Yeah, I think the left-hand side is a little bit blocked by the stuff, so I move to the center. Okay, so this is the entire configuration I'm going to use for that environment. So as you can see, it's just the putting everything in a slice together in a single file. So first, we're going to have several ports configuration that specify which subnet and which VLAN we want to use for this port. And then going down, we have several ports configuration. And then going down, you can see device configuration. This is the config block for 204, 205, 226, and 227. And then finally, it's the configuration for DHCP Relay, which specify the connect point and the server IP of DHCP server. That's it. That's all the honest configuration we need. So yeah, later on, this configuration will be available on the website, so you can go there. And so actually on the website, we also have it's a GitHub repository. We have a README over there, and we have a detailed step from the very beginning, how you fetch the code, how you install the mainnet environment, how you install Quagga DHCP server, and you can just follow that guide, and you should be able to bring up the mainnet environment very easily. So I already have Honest running. I already have my mainnet environment running. My mainnet is actually running in the VM of this laptop. So okay, try to make it larger. Hopefully that's good enough. So I have Mininet. So what I'm trying to do is that I'm trying to ping host 1 from host 3, right? So as you can see, the ping is going. And then I also have a TCP dump over here. So yeah, this is the packet dump on the first the port that host 3 attaches to. So as you can see, the port the host 3 is sending VLAN tag traffic with VLAN tag 30, and it arrived the switch. So I guess I don't have to just go through every hop, but the one good thing of trying to set up this environment in Mininet is that you can actually do port dump. You can do TCP dump on any port of the switch or host. That it's very helpful for debugging. Unfortunately, you are not able to do port dump on a physical hardware switch yet, but I mean, for development and also for if you just want to try out Trellis, Mininet would be an excellent environment for you to start with. So you can see, if your ping for some reason doesn't work, you can run TCP dump and follow the path of the packet and see where it goes wrong. So yeah, I think I don't have too much stuff to show. So I'll just end my demo here and see if there is any question. So please, if you have any question regarding the features, or you can also ask me the roadmap of Trellis or anything, please. Thank you. Oh, one last thing. If you want to learn more about Trellis, we post all the features I talk about today and all the documentation and instructions on this wiki page, which is the wiki.opencore.org. So make sure you visit this wiki page. All right. Questions? Please. Yes, IPv6 is fully supported in Trellis. I didn't show it just because I don't have enough time today, but all the IPv6 should work. So right now we support IPv6 for static IP configuration, bridging, routing, VLAN. It will all work. We also support DHCP v6 Relay. So an IPv6 host can use DHCP v6 to obtain an IP address from the DHCP server. We also support IPv6 router advertisement. So a host can also generate an IP address from the prefix announced by the switch, and combine with its own MAC address and generate IP address. That should work too. Excuse me, can you say that again? Yes, we need to configure loopback for the switch as well, but it's I skipped that part for my example today. It can be v6. It doesn't have to be v4. Actually, one of our customer, a service provider, they actually want a pure v6 environment. Yeah. Yes. Okay, good question. So to answer this question, I have to talk about two things first. So if you actually go to our website and follow the instruction of installation, you'll actually notice that we pull the Quagga code from the core code base instead of the upstream. The reason is that we have two patches that are not merged into the upstream yet. These two patches are, the first one is the patch for FPM, which is the one I mentioned we use to send the routing information to Honest. And then on top of that, we also have another patch that implement the keep live message on this FPM channel, such that if a quagga is down or goes away, Honest will be aware of it, and Honest will withdraw all the routes from that quagga. So these two patches are not ported to FRR yet, but if you really want to switch, I don't see any reason this can work with FRR, but it's just that we implement our patches originally on Quagga, and we don't see a priority to do the same thing again on FRR, so we haven't really moved forward to FRR. But if you are interested, I don't think there is any technical problem to move to FRR. Okay, any other questions? Sure. So I guess you're asking about like traffic slicing or isolation on the underlay, right? So we don't do it today. So for the underlay right now, it supports like best effort traffic plumbing. But as Saurabh mentioned, we are going to start the work of QoS very soon. And by the time, we should be able to share more information with the community. But right now, the current implementation of Trellis doesn't consider the partition or isolation of the traffic. But that should be possible because the switch chip does support that. It's just that we haven't exposed that feature in the control app. OVS control on the data plan. Do you mean that can we use OVS to form data? Yes, as I mentioned, the demo I just showed is run in Mininet using OVS. So my data plan is actually Open vSwitch. Is that what your question is? Okay. Okay. Yeah, but you need to use a slightly different driver. So if you look at the device configuration, you actually need to specify OFDPA-OVS. Okay, any other questions? No? All right, thank you very much for attending this track. Have a good one.